All right, so our project is called License Plate Anti-Z, which the name will be explained a bit later. So we built it with Taras and Kolya. This is a program that reads and recognizes license plates from the image of the car. Let's say, for instance, it's taken from CCTV cameras. So the main question of our research is whether we can recognize the license plates of the car, given that we have just one image of that car, where, of course, this license plate is visible on it. So the license plate recognition basically helps us to identify the owner of the car. And of course, that results into numerous applications that it can be used in. For instance, it can be used to solve the problem of breaking the speed limit or checking whether a certain car has entered a restricted area. But also, it can be useful during the war. And as you can see on the slide, we have this, ugly car with an ugly fascist painting on it with the mark Z. So during the first days of full-scale invasion, there were reports that some people in the cars were just riding around on the highways and putting marks for air tags. And of course, identifying such cars is extremely important. And that's like one of the reasons why we decided to implement the solution for this project. So it has 6 main implementation steps. So the first step will be to resize our image. And here we know that it is represented as a matrix of color intensity of every base color. The base colors are red, green, and blue. So the abbreviation for it will be RGB. So we can resize our image just as any other matrix. For that, we are using scale metrics with following coefficients, as you can see on the slide right now. And we have to multiply it on every single pixel of our image. The next one will be to grayscale the image. And grayscaling is probably one of the simplest tasks here, because we only have just one formula, which should be used to transform the RGB image to grayscale. And here you can see the coefficients are not like 0.333. That's a weighted formula for every pixel, which has to be applied for every point of on our image, and the coefficients depend on how we perceive these colors. So the next step will be to delete noises from the image. So the smooth surface of the car can often reflect various objects that we do not really want to take into account. And that is why we need to remove unnecessary noise from the image. Firstly, we tried to do that using simple blurring. And as you can see from the image on the left, it doesn't really help us a lot because we just take average from all pixels around the needed point, but the results are not what we need because the license plate itself gets blurred too. So that's why we tried a different approach called Gaussian filter. It takes into account distances between points. And that means that points that are further from needed pixels have lower influence than points that are closer to it. So it's kind of a blur but advanced. And the results after the filter look much better than from the simple blurring, as you can see on the image on the right. But it's still not what we need. So here you can see how this filter works on images with a lot of noises, which often are on images from videos, for example. So as we can see, it deletes these noises, but also blurs edges, which is exactly why we needed a different approach here. And that's why the approach that we eventually used is called bilateral filter. So bilateral filtering also takes a Gaussian filter in space, but it additionally considers one more Gaussian filter, which is a function of pixel difference. The important point is considered in bilateral filtering is that the 2 pixels are close to each other, not only if they occupy nearby spatial locations, but also if they have some similarity in the photometric range. The bilateral filter is controlled by 2 parameters: space parameter, which is denoted here as sigma s, and range parameter, which is denoted here as sigma r. So if range parameter increases, the bilateral filter becomes closer to Gaussian blur. But if we increase the space parameter, it smooths larger features. As you can see on the image here, This filter helps us to remove noises from the image when it doesn't blur edges, which is exactly what we need. So the next step will be edge detection. For that part of our project, we used Kenny edge detector, as you can see on the slide. That algorithm helps us to find the main contours on our image. So this algorithm consists of 5 different steps. The first one being noise reduction, which is already done by bilateral filter. So let's start from the second one. So the second step is gradient calculation. And in this step, we have to detect changes of pixel intensity. So the easiest way to detect those changes in both vertical and horizontal directions is to apply Sobel filter. And this filter uses derivatives to find changes in intensity of colors. So here you can see the formulas. The third step will be non-maximum suppression. The result from the previous step gives us thick edges, but we need to have them thin. So in order to achieve this result, we performed a non-maximum suppression. So the algorithm works in the following way. So if the pixel has the maximum value in edge direction from it, then we keep the pixel. Otherwise, we set the pixel to 0, which means we just make it black. So the fourth step will be double threshold. And here we are splitting our pixels into 3 different categories. We do that using upper and lower thresholds. That means that if the pixel has intensity higher than the upper threshold, then it will be white color, because it is a strong pixel. If the pixel has intensity lower than the lower threshold, then it will be painted black. And if it is between these thresholds, then we paint it gray. So the next and final step will be edge tracking by hysteresis. And in this part, we need to decide whether the weak edges are strong or not. The verification algorithm is actually pretty simple. We just check whether the weak edges are touching the strong. And if they touch, they're considered strong as well. And if they're not, we simply remove them by painting them black. So after these steps, we'll have all main contours of our image. After that, we can choose the 30 biggest and look at these contours. And we are looking for a rectangular one. And we assume that this one is actually our license plate. So let's look at the results that we had. Here you can see some attempts that actually were failed. So here you can see that the largest rectangular shapes, contours, were not the ones that were the license plate. And that's why our program detected them as the largest ones and assumed that they are the license plate, and eventually couldn't find any text on them. But don't worry, we also have successful attempts. So here you can see a lot more successful attempts where we could successfully find the license plates and eventually extract the text from there. You can see that on these images, there are a bunch of contours in the column that is before the last one. And you can see that on the last one, we actually have a contour for the license plate that was detected by the program. And thank you for your attention.